All right, so here we're looking at chapter 5, which is our gases chapter, and we're starting off with pressure. So we need to know about our units of pressure, and the first unit we're going to talk about is atmospheres or ATM. So in chemistry, when we talk about an ATM, we're not talking about going to get some cash. We do mean the atmospheres. And at sea level, our pressure is approximately 1 atm, and that's our room pressure. So in the room you're in right now, it should be right around 1 atm. We have another unit of pressure, and that is millimeters of mercury. And millimeters of mercury came from once upon a time when we really did have a tub of mercury. And yes, back in the days, way before my day, people would stick their fingers in to play with it. But the idea is the atmospheric pressure would push down. And when the atmospheric pressure would push down, the mercury level would rise. And they would measure this height that's labeled as H in millimeters. So that's how it got the name millimeters of mercury. So it is a measure of atmospheric pressure. And down here is a conversion that I do need you to know, and it's an exact conversion. And that is 1 atm equals 760 millimeters of mercury. We can also say that 1 atm equals 760 torr. So millimeters of mercury and torr are interchangeable units. Torr was named after somebody, I believe Torricelli from Italy. And millimeters of mercury came from literally measuring that column of mercury, but they are the same unit. So another way of saying that is for every 1 millimeter of mercury, there is exactly 1 torr. All right, so here are those units of pressure and a few more. So these are the units I want you to know. Those are the ones that are in the box. All right, so starting off is the Pascal. So 1.01 times 10 to the 5th pascals equals 1 atm. So I want you to know that conversion. Then 1 atmosphere is 1 atmosphere. Then millimeters of mercury, 1 atm is exactly 760 millimeters of mercury. And then torr, 1 atm is exactly 760 torr. And then we talked about a minute ago that 1 millimeter of mercury equals 1 torr. Okay, so there's a couple conversions down on the bottom that I don't need you to know, but I just wanted to show you these because you see them around. So pounds per square inch, or PSI, you see these on your car tires, on your bicycle tires. And then down below is one we don't use very often, but you know how Americans like the English system rather than the metric system. So while other people were measuring their barometer in millimeters, Americans were like, hey, we like our inches. So they would measure this in, or I guess we would measure this in inches. And so that's where we came up with the inches of mercury. So that unit we don't see very often, but it is out there. So we have pounds per square inch and inches of mercury. If I ever wanted you to use those, I would give you the conversion for them. So the only ones you need to have memorized are those ones in the green box, and I'm going to actually extend that to the 1 millimeter of mercury equals 1 torr, because again, those are identical units with just different names on them. All right, so next up we have the manometer. So a lot of times there is going to be gas and it's contained in here a bulb, or in lab it could be contained in your flask, and we need to know what the pressure is. And if we have an open-ended manometer, that means that there's an end right here that's open to the atmosphere. We can determine the pressure of the gas by looking at the pressure of the atmosphere. Now there's a formula right down here that says pressure of a gas equals pressure of the ATM plus the height difference, pH. I'm going to go ahead and say plus or minus, and I'm going to show you when it's plus and when it's minus. So I'm going to start off with 1, and let me zoom in here. Here the mercury, I have colored it in too, that's why it doesn't look perfect, but the mercury is at the same level on both sides. So if I thought about H, which is the difference in height between the two levels, I would say the height difference is 0. They are at the same level. So if it's true that they are at the same level, then I could say the pressure of the gas should be equal to the pressure of the atmosphere. So what's going on is the atmosphere is pushing down here, and it is exerting pressure on that mercury. It is trying to push the mercury away from itself. Then we have the pressure of the gas, which I'm going to call P gas. And the pressure of the gas is trying to do the same thing. It's trying to push the mercury away from itself. Well, if the height difference is 0, if they are at the same level, what we're going to say is that they must have equal pressure, equal force that they are pushing with. And we do have a lab that, should we do the wet lab, which I know we're not doing it this semester, you would use this principle to find out the pressure of the gas in your flask. All right, so here is another one. And here we have a similar situation. We got the pressure of the atmosphere, and it is pushing down. And we have the pressure of the gas, and that is pushing down. But the mercury is not even across the two. There is a difference in height, which we see right over here. All right, so in this case, I'm going to say the pressure of the gas is greater than the pressure of the atmosphere. And let me straighten out my greater than sign. All right, pressure of the gas is greater than the pressure of the atmosphere. The way I know this is the pressure of the gas is effectively stronger. Remember, this is sort of like hot potato. If you've ever played that game as a kid, nobody wants the mercury. Everybody's pushing it away from itself. Well, if the gas can push it further toward the atmosphere side, it means the gas is effectively stronger. It has more force, or we could say it has more pressure. So the pressure of the gas must be greater than the atmosphere if the pressure of the gas is able to force the mercury towards the ATM, towards the atmospheric side. So when that happens, I'm going to say the pressure of the gas equals the pressure of the atmosphere plus H. So when the gas is greater than the atmosphere in pressure, we're going to be adding the H to the pressure to find the pressure of our gas, because the pressure of the gas is greater than the pressure of the atmosphere. All right, so here is another one. And we have the pressure of the atmosphere pushing down. We have the pressure of the gas also pushing down. But remember, everybody's trying to push away from itself. Nobody wants to be near that mercury. And what we see is the atmosphere is doing a much better job. It's able to force that mercury onto the gas side. So here what I'm going to say is the pressure of the gas is less than the pressure of the atmosphere. So again, they're both trying to push the mercury away from themselves, but the atmosphere is doing a much better job. It's able to force the mercury onto the other side. So if I wanted to calculate the pressure of the gas, I would say it's equal to the pressure of the atmosphere minus H. And we're subtracting H because the gas has less pressure than the atmosphere. So let's just review these three situations. So if the height difference is 0, if mercury is at the same level on both sides, we say, hey, pressures are the same. Whatever pressure we get for the atmosphere, that is the pressure of our gas. But if that mercury is pushed towards the side of the atmosphere, we say, hey, that atmosphere is kind of weak. It's weaker than our gas. It doesn't have as much pressure. So the pressure of the gas is greater than the pressure of the atmosphere. And because it's greater, we're going to add H to find the pressure of the gas. And finally here, we have the pressure of the atmosphere, which is stronger, which is able to push the gas, or I should say push the mercury towards our gas. That means the pressure of our gas is less. It is weaker than the pressure of the atmosphere. And because of that, when we calculate the pressure of the gas, we're going to subtract out H. All right, so let's try a couple problems. Here it says calculate the pressure of gas in the following manometers. And we have atmospheric pressure at 782 millimeters of mercury. All right, so I'm going to start with this one on the left. The first thing I'm going to do is look at that mercury. Let me actually highlight it in a more appropriate color. There we go. It's a little easier to see now. All right, so we have the pressure of the atmosphere pushing down. We have the pressure of the gas pushing down. But what we see is the mercury is pushed towards the gas. So in other words, that gas is weaker than the atmosphere. It has less pressure. So I'm going to say the pressure of the gas in this case is less than the pressure of the atmosphere. So because of that, I'm going to say P gas equals P ATM minus H. All right, so again, because the pressure of the gas is less than the pressure of the atmosphere, we will be subtracting H. All right, so now let's do the actual calculation. We're trying to find the pressure of our gas, and I'm going to start with the pressure of the atmosphere. We're told it is 782 millimeters of mercury. And we're going to subtract out H. And for this problem, we're given that H is 18 millimeters of mercury. All right, so I'm going to take that 782 and let me straighten out my 8 a little bit. There we go. So 782, and I'm going to subtract 18. So it looks like the pressure of the gas is 764 millimeters of mercury. So we said the gas should have less pressure than the atmosphere, and that's what we found. We found a gas that is less than the pressure of the atmosphere that was given right up here. So the atmosphere is 782 millimeters of mercury, and the gas is 764. All right, so let's take a look at the next one. So here I'm going to highlight our mercury just so it's a little easier to see. All right, so in this case, we have our pressure from the atmosphere pushing down, and we have the pressure of the gas that's also pushing down. So they're both trying to push the mercury away, but this time the gas is winning. The gas is able to push it further away. Therefore, the pressure of the gas is stronger, or we can say it's greater than the pressure of the atmosphere. So pressure of the gas greater than the pressure of the atmosphere. And because it's greater, I'm going to say the pressure of the gas equals pressure of the atmosphere, and now it is plus H. All right, so again, when the pressure of the gas is greater than the pressure of the atmosphere, that is when you'll be adding H. So let's give this a try. All right, pressure of the atmosphere, 782 millimeters of mercury. Now I'm going to add H, and for this problem, our H is 24 millimeters of mercury. All right, so let's give this a shot. 782 plus 24. And it looks like we have 806, and let me straighten out my 8 again. 806 millimeters of mercury. So our gas at 806 millimeters of mercury is greater than the pressure of the atmosphere, which was 782, which is just what we wanted when we saw this picture where the mercury is being pushed towards the atmospheric side. So the gas should have a greater pressure because it's pushing that mercury away from it. All right, so next up, we're going to talk about standard pressure. All right, so standard pressure is normal atmospheric pressure, and we refer to it as 1 atm. We could also call it 760 torr or 760 millimeters of mercury. So that is our standard pressure. However, oops, sorry about that. It is more common to talk about STP, which will be standard temperature and pressure. So we're going to be doing a lot of gas law problems, and sometimes we will refer to STP, standard temperature and pressure. When we do, we are giving you the pressure and the temperature. So I need you to know that STP, or standard temperature and pressure, is 1 atm and 0 degrees Celsius. So this is going to come in handy for some of the problems that we're going to do later on. Oops. All right, next up we're going to talk about some of our gas laws, and we're going to start off with Boyle's law. So I know some of you took Intro to Chem and you may have some nightmares about all the different laws. I will show you how to put them all together. But for now, we're going to just start off talking about Boyle's law. And in Boyle's law, the volume of a fixed quantity of gas at constant temperature is inversely proportional to the pressure. So what we mean by inversely proportional is if one goes up, in this case the pressure is going up, then the volume needs to go down. Likewise, I could say the pressure is going down, and therefore the volume must be going up. And this is what I mean by inverse. So as one goes up, the other one must go down. And we can write that as P times V equals a constant. So let's just imagine you had a constant, let's call it 5, and you take the pressure up. Well, that would increase that constant unless you dropped the pressure. So the idea of this equation is it shows us that if you have pressure times volume equaling some kind of constant, and you mess with one of those variables, you bring one of them up, the other one must go down, otherwise your constant will change. So that is an equation just showing us that we do indeed have an inverse relationship between pressure and volume. All right, so as I mentioned, pressure and volume are inversely proportional. As one goes up, the other one goes down. So here I'm going to look at the pressure, and this is very low on the pressure scale. So looks like our graph starts at about 1 on the pressure scale, and this is very likely 1 atm. The units aren't given here. And here we have about 1 for the volume, which is probably in liters or milliliters. Now as we increase our volume, looks like we're at about maybe 3.2 over here at this dot. Notice that our volume has dropped. So as the pressure goes up, the volume goes down. So that's that inverse relationship. And the type of graph that we see here, if you were in algebra class, you would call it a hyperbola. And that is the kind of graph you're going to get anytime you have an inversely proportional relationship. So whenever you have a relationship like these right here, oops. All right, whenever you have a relationship like these right here, where one variable goes up, the other one goes down, you will get that hyperbola for your graph. All right, so for those of you who remember fondly or not so fondly Boyle's law, here it is. P1 V1 equals P2 V2. Now I'm not asking you to memorize Boyle's law because I'm going to show you how to derive it. And I know you guys probably have some nightmares of math and physics classes where you had to do that. But what I'm going to tell you is it's not that bad. We will take a look at that in just a little bit. But for now, we're going to see how it works. So here we have a diver, and the diver takes a balloon filled with 16 milliliters of air from the surface, where the pressure is 1 atm, to an unknown depth. So the volume of the air in it should be in the balloon. Originally, when I got this problem out of a textbook, the diver was taking a syringe under the water, which sounded very strange to me, so I changed it to a balloon, but obviously forgot to change the word in that, whatever it is, fourth line there. So the air in the balloon at this depth is 7.5 milliliters, and we want to know what the pressure at this depth is in atm. All right. So I need to label all of my variables. So I have P1, V1, P2, and V2. Now I like to consider 1, the initial conditions, and I like to consider 2, the final conditions. All right, so now let's talk about those initial conditions. So I need my initial pressure, and it looks like it is 1 atm. Next up, I need my initial volume, and it looks like it's 16 milliliters. All right, next up we're going to look at our final conditions. So we do not know what our pressure is. It's asking us what is the pressure at that new depth. So I'm just going to put a question mark here. I don't know what it is yet, but we will find out. And then V2, right over here, our new volume is going to be 7.5 milliliters. All right, so now we have all of our variables, and now we need to plug in. All right, so we're doing, P1 V1 equals P2 V2 like so, and we're just going to plug in here. So 1 atm times 16 milliliters equals P2, and I'm just writing P2 because I don't know what it is yet, times 7.5 milliliters like so. All right, so next up, I'm going to solve out for P2, so I'm going to divide both sides by 7.5 milliliters. On the right, that 7.5 will cancel. And we're going to calculate out what P2 is. All right, so 1 atm times 16, 16. All right, then I'm going to divide that by 7.5, and it looks like our new pressure is going to be 2.1 atm. And I'm using two significant figures because we had two sig figs from our atm and from our volume. All right, so couple things to notice here, and first of all, our volume is in milliliters. It could be in milliliters, it could be in liters, it could be in microliters. Really, it can be any volume so long as the units match. So whatever units of volume you have on the left, you need to have those on the right. Same thing is true for your pressure. So because I started in atm, I still have atm. But if you started in millimeters of mercury, you would end in millimeters of mercury. If you start in torr, you'll end in torr. So that one of the wonderful things about Boyle's law is it really doesn't matter what the units are as long as they match on both sides of your equation. All right, so here's our answer for our Boyle's law problem. All right, so next up we have Charles' law. So volume of a fixed quantity of gas at constant pressure is directly related to the absolute temperature in Kelvin. So direct relationship, here we're looking at volume and we're looking at temperature. So when volume goes up, temperature also goes up. Volume goes down, the temperature will also go down. So that's what we mean by a direct relationship, but that's something you probably know. So if you look at those balloons on the right-hand side, so the first balloon, this one right here, think about that as being at room temperature. And now over here they're pouring liquid nitrogen over it, which is extremely cold. But let's say you want to do this experiment at home. You just put your balloon in the refrigerator or the freezer. It's going to get smaller. So lower the temperature, the volume is going to decrease. Then you take it out of the fridge or the freezer, let it heat back up, and it might not expand all the way, but it will get larger. So again, our direct relationship means that as temperature goes up, volume is going to go up. As temperature goes down, volume is going to go down. All right, so volume of a fixed quantity of gas at constant pressure is, again, directly related to absolute temperature, and that temperature must be in Kelvin. So something I'm going to hammer home over and over, temperature must always be in Kelvin when you are using gas laws. So you want to just associate in your mind gases with Kelvin. So imagine some person, his name is Kelvin, and he is the gas master. He knows all about the gas laws. So somehow in your mind, just relate gas laws and Kelvin. All right, so then we have this equation right here. And it looks different than the previous one we've seen. And that is because we have a direct relationship. So let's imagine V over T is some constant. Let's say that constant is the number 1. And let's say currently we have 5 for our volume and 5 for our temperature. Well, if you increase that volume and instead of 5, now you have 10, you just messed up that constant. It no longer is 1. So you're going to now have to increase your temperature to match so that you still get 1 for your constant. Likewise, if you had, let's say, a volume of 2 and a temperature of 2, but you decided to decrease your volume and now you've made it 1. Well, you've just changed your constant. Now that's 0.5, and you can't do that because a constant's supposed to stay stable. So to preserve your constant, you're going to have to decrease that as well. So here what we see for our direct relationship is we have one variable divided by another equals a constant, and that represents our direct relationship. We call it directly proportional. All right. So here again we're talking about Charles' law, and the volume of a fixed amount of gas at constant pressure is directly proportional to its absolute temperature in Kelvin. So here's our volume and here's our temperature. And notice down here, they're both relatively low, but right up here, they both get higher. So as one increases, so does the other, or we could say as one decreases, so does the other. So whenever you have a directly proportional relationship, oops, that was a little on the dark side, directly proportional relationship, it will plot out as a straight line. All right, this is a whole slide dedicated to something very, very important. We already talked about our buddy Kelvin, who knows everything there is to know about gas laws. Whenever you are in gas laws, your buddy Kelvin is going to be used. So you must be in Kelvin when you're using gas laws. All right, so next up I'm going to show you a YouTube video, and then we're going to come back.
Cold cuts, no baloney.
Just science.
Hi, I'm Joanna.
And I'm Steve.
And this is a container of liquid nitrogen.
And this is a really big balloon.
Let's see what happens when we place the balloon in the liquid nitrogen.
Okay. Whoa, wait. Isn't the balloon gonna pop?
We'll see.
Oh, man. Huh. Okay, so the balloon didn't pop. There's obviously a hole in the balloon somewhere because the air's leaking out. So maybe instead of popping, maybe the balloon just got really cold and it cracked like an egg, and all the air is slowly leaking out of the crack.
Well, if that's the case, what's the balloon going to do when I take it out?
Nothing. It's a balloon with a hole in it and all the air's gone.
Well, I'd say the air is still in the balloon.
So where's the air?
Right there.
That's water.
Nope. If that were water, it'd be frozen solid. That's liquid air.
What?
When we place the balloon in the liquid nitrogen, the air inside the balloon gets really cold. When particles of a gas get cold, they start to slow down and take up less space. If we can get the gas cold enough, we can change it from a gas to a liquid. That's what happened inside the balloon. We changed all the particles of nitrogen and oxygen to a liquid.
So how do I get my balloon back?
We just have to place it someplace hot, like the table.
Oh, so I get it. Now the reverse is happening. The heat from the table is making the liquid air inside boil. When a liquid boils and changes to a gas, the particles move faster. When the particles move faster, they take up more space, and the balloon gets big.
Exactly. Thanks for watching. I hope you'll join us again soon for another experiment.
Try that again. Not that side.
All right, so the last thing that I want to talk about today is our different laws, Boyle's law, Charles' law, combined gas law, Avogadro's law, and our Gay-Lussac's law. So back in Chem 2, you might have had to memorize all those formulas. So what I'm going to tell you is you do not need to memorize the individual formulas, but what I do want you to know is this formula right over here, PV over NT equals PV over NT. So it sounds crazy, but that one formula will get you any of the other formulas. So what we'll be doing, and we'll be practicing this next class, is that you will cross out anything that you don't need in that equation, and you will be left with any of those other equations. So just to give you an example, let's say you have a problem in which the number of moles don't change and the temperature doesn't change. You are left with Boyle's law, PV equals PV. So that's how that equation is going to work. And again, we're going to get more practice next class. But I wanted to ease your mind a little bit and let you know you didn't have to memorize all those individual laws. The other thing that I do need you to know from here is the ideal gas law. So this is going to be very important. And this is PV equals nRT. So you still have to know two gas laws, two formulas here, but you don't have to memorize all those individual ones. And we're going to get more practice with this next class. So thank you for joining me, and hopefully I will see you soon.